Chen. I'm responsible for Sepax column applications and the tech support. I want to thank everyone for joining us today. In today's webinar, I would like to discuss the analytical characterization of antibody drug conjugates. We'll be talking about some of the challenges and the solutions. Even though we're talking about analytical solutions about antibody drug conjugates, all the column phases we talk about today here can be scaled up to the semi-prep and the prep scale with either larger column volume packing or with larger particle size for your semi-prep or prep scale, depending on the purpose of your separation. So let's talk about antibody drug conjugates a little bit. So antibody drug conjugates, it is also known as immunoconjugates. It is becoming a very important drug category, actually the protein therapeutics for the cancer treatment. There's some of the background information here. As name indicates, ADC is actually composed of the antibody, as you can see the Y-shaped, and then the small drug attached to the antibody, and then the linker chemistry linking between the antibody and then the small drug. To make ADC work for the cancer therapies, MAB is really specifically for the target site specificity. And the drug, the small drug here needs to be a high potency and also have a valid mechanism of action. The linker chemistry is also important as linking the drug to the MAB through different conjugation sites. We're going to be talking a little bit about those later. And it needs to be stable, but also, needs to have a release mechanism once, upon the internalization to release the drug. So for the conjugation sites, we already have 2 drugs on the market for the cancer therapies. They include the traditional ones. It's the lysine conjugates, and then also the cysteine conjugates. These are 2 the very popular ones. However, there are also other ones as well. So for the lysines, actually, you can imagine there are so many lysines in the one MAB molecule. And actually, it really creates the heterogeneity when you really conjugate the drugs to lysine, because you can really control how many drugs conjugate to those, surface exposed lysines. For the interchain cysteine residues, as we can see here, we can have the heavy chain, light chain, the disulfides. They are 2, the one each on each side, and also the 2 disulfides in the hinge region. So with the partial reduction, you actually also can have heterogeneity, but it's with much limited numbers of drugs attached to the molecule. So what you can have is 0, 2, since it's disulfides are paired, so you have 0, 2, 4, 6, 8 drugs conjugate to the molecule. Also, the glycans actually can be conjugated as well with the drug, so with the oxidation of the carbohydrates. And also right now, a lot of people are talking about, using the special engineered amino acids to really control the, drug antibody ratios to limiting like very defined numbers. There are also discussions using the glutamines residues with enzymatic reaction to conjugated drugs with 1 or 2 drugs, or 2 to 4 actually is 2 drugs per linker chemistry. And also the next generation, also there's mentioning about unnatural amino acids being incorporated into the monoclonal antibody to have the drug conjugate to those amino acids, and then which really give you defined DAR ratio, and also the monoclonal antibody structure is less disturbed than those lysine and cysteine conjugates. So for any of the given ADCs, the chemical property of the attached drug and the linker, along with the conjugation site, definitely will have the effect of the, some of the attributes of the ADC as a whole. So we'll be going to the analytical methods for ADC characterization we're going to cover today. First, we actually will go into the intact ADC variance characterization. So the methods are already being applied for the monoclonal antibody. However, due to the drug attached to the monoclonal antibody, there are some differences. The profiles will tell you different informations, other than the MABs as well. And then the unconjugated free drug analysis. The drawback, right now, you have the reverse phase, and then you have a sample prep, precipitate maps influenced by the buffers, excipients in the formulation, and also the incomplete protein precipitation. So in this case, in our presentation, we're going to introduce a C-line Xenic SEC 80 angstrom pore. It's the smallest pore size we have on SEC. Show some examples of how we do the free drug analysis. As we mentioned, you have many drugs attached to the monoclonal antibodies. So drug-antibody ratio assay is very important to determine the average of the DAR and also the DAR distribution. For the DAR, average DAR, there are methods of UV-Vis spectra ADCs using a different maximum absorbance wavelengths for these, the drug and the antibody. In our presentation, we'll be talking about hydrophobic interaction chromatography for individual DAR species analysis and also the average DAR calculations. And also this can be applied to the stability assays of those ADCs as well. And also we'll be talking about the reverse phase using the subunit analysis to see how we can take a look at a different drug attachment to the the heavy chain, light chain, and use a mass spec friendly mobile phase for the detection. The subunit, as we mentioned, we also the reverse phase. It's a polymer-based reverse phase column. And also, IDAS, it's a very defined digestion of the map below the hinge region. So we want to sort of take a look at these fragments as a case study, use the SEC and the HIG and the reverse phase to see the separations of those fragments. And then we'll go into conclusion and the Q&A sessions. So first, let's go into the SEC analysis of the map and the ADCs. So a lot of people will naturally take the columns worked format, and then we use that for the ADC analysis as well. So let's take a look at some of the analysis between, what's the difference between the map and the ADCs using the traditional SEC. And also we do have our modified surface, the C-line, for the specifically ADC analysis. On the right panel, you can see actually it's a Herceptin map, and then you can see it's very nicely resolved between the aggregates and then the monomer, and there are also some of the low molecular weight fragments separated. The resolution between the monomer and aggregates is great, it's 1.9. However, when we put on the Herceptin lysine ADC onto the SEC, as you can see, the blue trace is the traditional Xenic SEC, and can see it's really much more of the tailing and a reduced recovery. This is under the native condition, 150 millimolar phosphate. There are also a lot of literature talking about, if you run SEC, the traditional SEC with the ADCs and under the native conditions, you do get this kind of profile. And then you have to have the additives to remove these interactions to have much better peak shape, better recovery, and better resolution. In our case, we actually just switched between the traditional SEC to our modified surface Xenic C SEC. 300 angstrom pore is the most suitable pore size actually for the ADCs, and the map is for the 150 kD molecular weight there. So as you can see here, just by switching the phase, we minimize the hydrophobic interaction between the sample and the resin surface. It is due to the nature of the hydrophobic nature of the small molecule. All right, so what's the difference between the C-line and the non-C-line? We'll take a look at the SEC phase structures. On the left side, this is the stand-up monolayer, covers the silica surface, to minimize the interaction. So that actually the left stand-up monolayer actually works for most of the, your regular maps and, Fc fusion proteins, any other proteins. However, with the ADC, due to its hydrophobic nature from the small drug gives the hydrophobic nature for the AD whole, it does give you much more of the interaction. So the C-line has a longer chain. This chain flats on the surface, has more of the protection for the resin surface, from the the sample. So it's really suitable for the C line, suitable for the ADCs and hydrophobic. Any tough samples, super sticky proteins, it's already been used for a lot of ADCs, hydrophobic mAb, pegylated proteins and membrane proteins especially as well. So for the C lines, if you have the ADC samples, I would say directly go to the C line, which will minimize the interactions, the hydrophobic interactions between the sample and then the column. We also have the 10 micron resin in the for the semi-prep and the prep skills. So if you find out that Zinc C is really suitable for your analytical purpose, you can actually scale up your purification using our 10 micron, the SRTC 10 micron for the semi-prep and the prep scale purification. All right. So there are also a lot of people use, a lot of ADCs. Every sample is different, so you have different salts, to minimize the different interactions or keep the, molecule happy. So in this case, you want to see. We have seen some people using potassium phosphate and then chloride, potassium chloride, 200 millimolar each in some of the separations. For this specific Herceptin lysine ADC, it's actually the 150 millimolar phosphate. Gives you better recovery and a sharper, much sharper peak. So I would say, with individual samples, you probably should take like a different salt concentration, different salt additives as well. So next we'll be actually talking about a few of the mobile phase additives. In this case, this is not, the parent mAb is not a Herceptin, it's a different mAb, but it is a cysteine ADC with an average of 4 DAR, and then distribution is also 02468. The profile on a traditional ADC, it's very similar to the one we have talked about. The Herceptin lysine ADC is with more of the tailing, lower peak shape. But when we switch to the C line, as you can see, the A trace, it has very nice symmetrical peak here. And we wanted to evaluate some of these mobile phase additives to see the impact on the SEC separation. So first we have tried with the arginine addition. Arginine is known to disrupt hydrogen bonding between the resin and then the sample. So we added a 200 millimolar arginine into the 150 millimolar phosphate buffer. As you can see, it didn't really change much, and these are the resolution, tailing, aggregation, monomer percentage here. The acetonitrile is known to disrupt hydrophobic interactions. You can see in this case is the C trace. You can see the recovery is much more improved, the peak shape. If you move down these traces, you actually can see bigger peak shape, and also the resolution is kind of similar to between aggregates and the monomer, similar to the B and A buffer there. But the recovery is improved. And then sodium perchlorate, it's actually a chemotropic agent. It's known actually to disrupt hydrophobic interactions between the proteins. At very high concentrations, the chemotropic agent can really dissolve insoluble proteins. Often they are used in the protein refolding. But in our case, we are at a much lower concentration. It can really minimize the protein-resin interaction, really to improve the separation. So if you look at the parameters here, the resolution, the tailing, and then the percentage of the aggregates and the monomer, you can see in this case, sodium with the 200 millimolar addition of the sodium perchlorate, you get a much more of the the total protein recovery, improve the resolution, and then improve the tailing factor of the monomer peak. Of course, we talk about all these additives to improve our LC, peak shape, the tailing factors, but also these additives need to be evaluated if it changes the protein conformation or the stability. So another orthogonal method, should be added to confirm whether these additives change the protein, and then if this protein stays the same under these conditions. So more evaluations, on your end with the molecule you have, it needs to be evaluated when you're adding all these additives, if anything can change. Okay. This is just a comparison with another vendor's column. Just give you some idea how it looks like between the two columns. Of course, maybe the buffer system may need to be optimized on each column, but in this case we used 150 millimolar phosphate using a lysine ADC. Actually, you can see our column has a much sharper peak and with better resolution. It's just with a similar tailing factor, a little bit higher peak area. And also, a lot of people use, SEC for LCMS to determine a lot of intact map mass and also intact Herceptin lysine ADCs. For cysteines, actually, due to its non-covalent linked, subunits, once you have the drugs conjugate to the map, it will dissociate into different subunits with some of the disulfides still intact under the non-reducing but under the volatile denaturing mobile phase here. So in this case we have 0.1% TFA, 0.1% formic acid, and 20% acetonitrile. We are able to get a intact mass for Herceptin. It's about 148 kD. Then the lysine conjugates, we're able to see up to 5 drug conjugates. The Herceptin cysteine, here, as I labeled, there are a few combinations of subunits here. Can go into a little bit detail here. These are the possible different cysteine ADC components under acidic and denaturing condition without the reducing conditions. So you can see, with 2, 4, 6, 8, these are the possible combinations of subunits. And now, if you're fully reduced, so all these disulfide bonds will be broken. So you'll have all these subunits. So under fully reduced conditions, you have the light chain 0, heavy chain 0, light chain 1, heavy chain 1, 2, 3. So here's the cysteine ADC SEC. Just inject your intact cysteine into the SEC. You actually can have these separations. So the number 4 is the lysine, not lysine, sorry, it's a light chain with 1 drug conjugate. The peak 3 is actually the heavy chain with 3 drugs conjugated, and the peak 2 is the 1 heavy chain with 2 drugs and with 1 light chain conjugated with connected with the disulfide with 0 drugs, and peak 1 is the 2 heavy chain connected by a disulfide with 1 drug on each chain, and there is a slightly bigger species we have to resolve there. So so we got those masses with the 0.1% TFA, and a lot of people just especially mass spectrometrists, want to have a lower TFA. So we have tried a 0.05% TFA and a 0.1% formic acid just to take a look at the peak shape from the SEC profile. You can actually see with the integration, the peak area did not change. It's just the peak gets broader, but I think it's good for the mass spec already. You can further decrease the TFA to keep the peak shape nicer. I think the 1%, sometimes you need to increase to 1% formic acid to do that. Immunogen scientists actually published a paper detailing really varying a lot of these concentrations of these TFAs or formic acid, acetonitrile percentage to see how the distribution of your protein envelope, the charged states, how they affect the charged states, and to get the DAR ratio affected by those charged states as well. So, and also there are some other acetic acid and then the HFBA acids being evaluated. So it's a very good paper to take a look at. Those are the parameters. When you have your ADCs, it's probably nice to you'll be evaluated, and also to take a look at what's the difference from the mass spec, the charge envelopes, the final deconvoluted masses, especially for the drug conjugates. And of course, we have mentioned the cysteine ADCs, dissociates the non-covalent bond, the subunits dissociates under the acidic denaturing conditions. So a lot of people will try to get into the native condition with volatile salts. So in here, as a proof concept, we have tried a 200 millimolar ammonium acetate on a 2.1 by 300 millimeter Xanax C column. Actually, you can see it's separating pretty well. I mean, in comparison to the 150 millimolar phosphate buffer. Of course, mass spec needs to determine what, whether the charge envelopes looks pretty, and also deconvolution, come out at the correct mass there. All right, so we have talked about SEC on the size variance and on the LCMS related applications. Next, we'll go into the antibody drug and the free drug analysis using our smallest pore, the AD angstrom. So the detection of the free drug is actually very important in product safety. It is really, highly toxic. It's an efficacy, the safety issue there. So sometimes the residual amounts of the unconjugated drug or drug-related impurities may still be present due to the incomplete removal by purification steps, in the conjugation mixture. And also these free drug or the broken down drugs can occur during the ADC storage. So it is also the free drug analysis is part of the drug stability in the analysis in the biological fluids such as the plasma or serum samples. There are some methods of reverse phase, with direct injections. Since you have just such high protein amount, it may clog the column, and there's also SPE and or the protein precipitation. It will probably sometimes have incomplete removal of the proteins. So in our case, we'll actually take a look at this very easy SEC and also mass spec-friendly separation. What we have done is, since we are lack of the real sample mixture, what we have done is that with the ADC sample, we spiked in some of the free drug paclitaxel. And then this separation here, as you can see, the drug came out after the column volume. It really, in this case, the hydrophobic nature of the drug really plays to our favor for the separation. It retains on the column a little bit longer than the whole molecule. So we're able to well separate these two species, the free drug from the very large molecules. And also we are using the volatile buffer for the separation. And the acetylnitrile percentage, you can play with the different percentage and then, the different salt concentration. It really depends on the hydrophobicity of your drug. And then sometimes people do 2 drugs per molecule, so depending on different hydrophobicity of the small molecule, it can be well separated on the one column as well. With the quantitation, you actually can do a standard curve using the small drug, different concentration or different amount of injection, generate a standard curve, and then you can calculate how much of the residual drug is still present in the sample mixture. All right, so that's very quick and easy. Next, we'll be talking about ADC charge variance separation on the cation exchange. Cation exchange chromatography is actually a very routine method for map charge variance study, such as lysine variance, deamidation, and also oxidations and terminal pyroglutamates formation. But due to the drug linkage to the map, the conformation of the protein may be changed dramatically. So some of the information you are getting may not be similar to of the map charge variance there. Especially for lysine conjugates, lysine carries a positive charge. So for each lysine conjugate, you will decrease 1 positive charge. IEX may reflect more of the drug loading information rather than providing information on the map protein molecule. However, I haven't seen a lot of publications on using the CEX cation exchange for the ADC charge variance study. However, we do see a lot of customers using the CEX for their current charge variance study, and some of the profiles being really nice, successfully monitoring the charge variance of the ADC samples. So let's take a look at, 2 ADCs. That's, the parent or the naked masked Herceptin, and then the ADC, the 1 and 2 is 2 very different small drugs, and the linker chemistry is also different. You can see it really resolves, it gives a very different profile, charge variance profile under the same condition. So in this case, Herceptin, you can see there's a different separation here. I have to mention, if you have optimized conditions for the MAP, monoclonal antibody charge variance, it may not give you the best conditions for the ADC charge variance separation. In our case, Herceptin, actually we have a really nice pH gradient for this monoclonal antibody, but we cannot resolve ADC well, or not as well as in this case we're using a Hippies buffer at a pH 7.2. So you can see, it lines up very nicely with unconjugated main peak. still residual unconjugated map in the ADC sample, and all the other different the charge variants due to the conjugations of the small drug on the linker chemistry. So sometimes if the linker chemistry have the charges, then it may reflect on your charge variance as well. And sometimes you have the in the chemistry portion, you have the ring opening and introduce the charges. It also will reflect from the cation exchange as well. So this is the strong cation exchange. And I want to take a look at it. So weak cation exchange, we have SCX and WCX offered as a monoclonal antibody screening kit. In this case, it also can be applied to the ADC as well. This is the weak cation exchange. You can clearly also see the unconjugated map here, and you can see the different charge variance peak. This is a comparison with the ADC2. You can see actually these two peaks here, the two smallest unconjugated map, it's give you different selectivity and give you different, slightly different peak profiles. For really understanding what are those peaks, really fractions can be collected, and then further doing reverse phase for the peptide mapping to determine what are the changes caused by the antibody drug conjugates, or during the storage, or during the process, what happens to the changes to the ADC molecule. And of course, we are talking about ADC, cysteine ADCs and lysine ADCs, as I mentioned before, with each lysine sites conjugated to the drug, you will lose a charge, and it doesn't really resolve well a lot of times on the IEX here. But in this case, we still can see the unconjugated map, and then further method can be improved with the, to further separate those, I would say the peaks of the bigger mountain here. I haven't seen really a lot of positive literature about the lysine conjugate separation on IEX, but we do have customers using that to monitor their molecules. And I think Immunity had a once presentation on the lysine conjugates with the cation exchange separation. They do resolve their peaks much better. Very good. All right. So we're talking about charge variance separation on the cation exchange, and next we'll go into the hydrophobic interaction chromatography for the DAR analysis, the average DAR calculation, and also the DAR distribution. The column we'll be using is a polymer-based hydrophobic column. It's a butyl phase. We have the example here with the butyl phase. However, we don't offer a screening kit with the ethyl propyl butyl phenol attached to the resin, so give you different hydrophobic columns to screen your ADCs, because sometimes the small drug has different hydrophobicity, which leads to the different hydrophobicity of the ADCs. So not all the time the butyl is suitable, and the other phases may be a better choice. Right. So again, the same the two ADCs with two the parent map is the Herceptin with the two different drugs or two different linking chemistry. You can see the hydrophobic interaction column resolve these different drug ratios differently. Now in this case, this ADC1, the distribution you can see very differently. So it may be possible here's a 2, 4, 6, maybe 6A, things like that. In this ADC2, clearly in both samples we can see the unconjugated map here. And then this is a D2, 4A, 4B, and a 6 and 8. So in this case, cysteine ADC2 has a DAR about 4. So what we can do is you can calculate the average DAR ratio here. We actually integrate all the peaks of these the peak using the peak area in this formula to take a look at the DAR. We actually calculate about 4.1. So it's very close to the number where we were supplied with. And also, there are a couple of columns on the market. We are just head-to-head comparison with another butyl column on the market. As you can see here, our column can separate much, pull apart a wider maybe some of the isomer better with a different drug load species. Of course, you can see here we added an IPA, so these are the concentrations you can modify if you have different drug conjugates, because you may not need that high, or you can go higher. It really depends on different the ADC molecules to give you the better separation. Of course, different Higgs phase will also give you a different separation profile depending on the hydrophobicity of your molecule. And in the next section, we actually will be talking about collecting some of the peaks and then to reduce the sample and then to run on the reverse phase to see the different the subunits, how the drug loads conjugate to those subunits. All right, that's the Higgs. Let's move on to the intact and reduced the MAB ADC fragment separation on the reverse phase. What we have here is the polymer-based reverse phase with 1,000 angstrom ports, so very suitable for very large biomolecules. As you have seen these slides before, so these are the possible different cysteine ADC components under the denaturing condition, but it's not reduced. So reduced, fully reduced, you only have 1, 2, 3, 4, 5, 6, the L0, H0, L1, H1, H2, H3. But with not reduced, you have many, many different possibilities. Not necessarily all in a sample, but maybe the possibility is there. So we have the Herceptin based on our mass spec. The light chain has a 23 kD. The heavy chain has about a 51 kD. This is the MAP Herceptin, and then with the two cysteine ADCs we have talked about before. As you can see here, it's very nicely separated with unconjugated, and then two ADCs with the same naked map but exhibiting kind of a little bit different profile. I think it's due to the different hydrophobicity of the drug, which gives a different hydrophobicity of some of the fragments or fragment combination there. Some of the method development, you can, this is the G1, the gradient one, that's what we initially started out, and then when you increase the starting percentage of the acetonitrile and then stretch the gradient longer, you are able to pull these peaks apart much better. And then you can, this is a 4.6 by 100 millimeter column. You can load more samples, even though we only loaded 10 microliter for some of the separation. For reverse phase, often people tell me, the carryover, especially for large molecule, is an issue. So what we have here is we inject a blanket injection after the ADC these samples, and you can see it's pretty much flat, during the separation region, and I think we can really say the minimal sample carryover in a blanket injection after the sample run. And then how do we look at it? We just want to give you some idea the lysine conjugates due to the many heterogeneity or many, many different lysine conjugates. You won't get as pretty the separation as the ADC, the cysteine ADCs, but clearly unconjugated map can be seen here. This is actually just our first gradient. You actually can further improve the gradient to further separate the unconjugated map and maybe resolve these much more, but these are the many, many, many different ADC variants. They are depending on a different hydrophobicity. So for the previous separation, the cysteine ADC on the 4.6 by 100, we also have tried on the 2.1 by 50, and also have done the mass spec analysis. This is the injected intact cysteine ADCs and without any reducing conditions. As we can see here, the peak 1 is actually lysine with 1 drug conjugates, and this star is unconjugated map. We have the overlay there. And then 3 and 4 is a mixture of the different fragments as I have shown in that graph there. Number 5 is the heavy chain with 2 drugs and the light connector with the disulfide. And then number 6 is the heavy chain with the 3 drugs there with the highest hydrophobic nature in this separation. All right. A little bit, just give you some idea on the mass, deconvoluted mass there. So the peak 1 is the light chain 1 with 2, 4, 3, 6, 3, and then in the peak 5 is the H2L0 based on the drugs with the linker, I think is about 925 Daltons. You can add up to this combination of the subunits. So it correlates very well with the theoretical mass there. Of course, with 2.1 by 50, you actually can run much higher flow rate with the, relatively low pressure. You can have a faster analysis. We have modified a little bit of gradient, and then the whole run, from the injection to recreation, ready for next injection is about 10 minutes. Of course, this can be in line with the mass spec. We also did reducing conditions using the, reduce the entire the map and the ADCs, and then subject to the reverse phase separation. Here also we use 2.1 by 50 millimeter. What we can really see is different subunits. As I mentioned here, fluid reduced. You have light chain 0, heavy chain 0 here. So Herceptin, you can see heavy light chain, heavy chain. And then in the cysteine conjugates, you can see the light chain 1, heavy chain 1, 2, 3. And these are probably some of the different heavy chain variants there. And then the lysine ADCs, again, due to the different conjugation, different great degree of heterogeneity, you'll see many, many different peaks. So if you want to do extended, the column length to have better separation, you can do 2.1 by 100 or 2.1 by 150. And if you want to do higher loading, you can go up to the 4.6 by 100. Or we can also pack it into the other dimension of column as well. So we have mentioned in the HIC section, you can collect different peaks and then reduce the peak, reduce the fractions, and then run on the reverse phase. So in this case, we injected, actually this is a 10 microliter profile, but we injected 30 microliter, collect this star, the red star, the peak, and then concentrated with the acentricon, and then did a reduction, and then run on the reverse phase, and it overlays very nicely with the light chain 1 and a heavy chain 1 with one drug on each. You can see this is the reassembled the drug loads there. In one of the Genentech's paper, they actually used a larger HIC, and then with I think it's about a 1 mg, at least 1 mg ADC loading, and then you can collect all those peaks and reduce, and then you can run different fractions and then see the overlays of these different subunits and with different drug loads. Of course, right now there are 2D LC as well. What you can do is you also can have the first dimension as a HIC, and then using the reverse phase as a second dimension, use a hard cut, introduce the fractions into the reverse phase. However, it's not reduced, so you will be getting all the other different combinations of subunits connected with the disulfides if they're not reduced. All right. So also, people, can we lower the TFA? Of course we can, but also you are compromising the peak shape. In this case, we tried a 0.1%, 0.05% TFA, and a 0.02% TFA. As you can see here, 0.1%, 0.5 still doable, but 0.02%, it really gives you much broader peak. So probably more of formic acid can be added to improve the peak shape, but on the other hand, we have obtained the mass spec just using a 0.1% TFA there. So that it's very well. And then column temperature effect, you probably have noticed a lot of our runs has 80 degree. This is a lot of times necessary for very large biomolecules. Just want to give you some idea, like BSA, you say, well, we don't really need it. Yes, I mean, at 25 degree, you get really, nice separation, normal peak, and 80 degree, actually, you have more of the probably sample change there. But with the map at 25 degree, you don't have the illusion. When we increase to 80 degree, you get a much better resolution between the intact map and some of the other impurities. And for the ADCs, interestingly, once you conjugate to the map, actually at 25 degree, you actually get some of the separation. But once we increase to 80 degree, you get more of the resolution, the recovery. We had done another with another molecule ADCs, and I have tried 25, 40, 60, 70, 80, and for that particular molecule, actually 60 degrees enough to have the really nice separation with optimized gradient. You can really have nice separations of those different subunits and subunit combinations. So for each individual ADC, I kind of recommend you can start out maybe 40 degree and 60, 70. Just take a look at different temperature effect on the separation. Next, so just as a sort of a case study, we have heard a lot lately about iodized digestion because this enzyme is very specific. So I want to take a look at those fragments, how it separates on our SEC HIC and also the polymer-based reverse phase. Just a little brief overview about where does the IDAS cuts. IDAS actually cuts only the IgGs, IgG1, IgG2, 3, 4, and also the fusion proteins as well. You can see here it cuts really below. These are the sequence here, very specific sequence. You cut below the disulfide, the hinge region, and you get a half of the FC, and after the DTT reduction, you get a light chain and also the 25 kD so-called FD. So for ADCs, since this portion is not conjugated in the case of the cysteine conjugates, but so you're getting the only this portion is conjugated with the drugs. So it's simplifying actually your molecule and then give you less of the headache for the mass spec. In this case, we have tried the fragate IDAS resin, or also the Promega, the liquid IDAS. Both of the product worked really well. The digestion buffer is just neutral, 10 millimolar phosphate with 150 millimolar sodium chloride at a pH 6.6. This is just under the native conditions right after the IDAS digestion. You can see this is a map, intact maps. It's 150 kD, and then 2 is 100 kD with the FAP2 very nicely resolved from the unconjugated, and the reaction is pretty complete. And then the 25 kD, the half of the FC fragments. Also, we'll just take a look at those different fragments on the under the denaturing condition, the mass spec. We can see the intact Herceptin is about 148 kD, and then reduced heavy chain, light chain. Mass is determined, and a FAP2, and then the half of the FC there with the mass determined as well. Due to the closeness in the molecular weight, the FD and the half of the FC is not resolved, but you can determine those masses from those peak, and maybe a smaller pore may be applicable to this specific sample mixture. Also, we have tried onto the HIC column. The condition we did not optimize. We just basically took our intact ADC gradient. We just ran the same, and you can see it's interesting. The half of the FC and the FAP2 is resolved pretty nicely. I think if you extend the gradient, you can have much better separations as well. For the assisting ADCs, since I've mentioned that the FC portion is not conjugate with the drug, you still have the pretty big peak. But the FAP2 is conjugate with the drugs, with different form, different number. That peak is greatly reduced, and you have more of the different FAP2, different drugs. So it'll be interesting to analyze these fractions and then to see what are the, it's another way of characterizing the different drug conjugates on the FAP2 region. We also tried to reduce it. After IDAS digestion, we added 4 molar guanidine, and the samples reduced with, sorry, there's a typo here, is reduced with 20 millimolar DTT for half an hour at 56 degrees. So you can see the different the fragments here, and also with the Herceptin cysteines, also very, with different drug conjugates. And it's interesting, you get more of the information and much slightly better peak shifts with the Herceptin lysine in comparison to the other just directly reduced. So you can see probably the FC portion is also conjugated in this case because split into 2, and you have more of this peak here. So it would be nice to continue, to characterize them with mass spec to see those drug conjugates. All right, so we have talked about all these phases. We'll go into the conclusion. First, we have mentioned the Xenic C SEC phase offers a better recovery and a separation of the antibody drug conjugates. And a lot of these drug conjugates has secondary interaction with traditional resin surface due to the hydrophobic nature. And we also talk about a little bit about the additives to improve the separation. It really depends on individual ADCs. You can try those organics, chemotropic agents, and arginine, all these additives to improve the resolution. So smaller pore size than CSEC, we found it's very beneficial in our free drug analysis. Our charge variance study, so we have talked about SCX, WCX, really can provide charge variance study for the antibody drug conjugates. The conjugate and the free map can be separated. Also, these different peaks need to be further characterized and to really understand what's different there. The Hick phase allows the DAR calculation and the drug distribution analysis, especially for the cysteine ADCs. Right now, a lot of customers using Hick, for lysine ADCs, you actually can separate unconjugated and with the conjugated, and there are different purposes there. The polymer-based reverse phase chromatography provides really high throughput resolution and fast analysis for the intact map, ADC fragments, and with online mass spec capability. So unconjugated map also can be readily separated from the ADCs. So all the techniques we talk about is, the examples we showed is just with the antibody and the small drugs. However, there are a lot of other sample types with the antibody conjugates. For example, the dye conjugates, antibody peptide conjugates, or any other antibody conjugates. All the same principle should, you can follow and for the method development. Here are some references, very good reference, for you to read. If some of you just get into the ADC research work, these are some of the nice review paper, and some of the methodology we have talked about is, from these papers. So, highly recommend you take a look at those. Here's the product information. So some of the products we are talking about here, some of the different dimensions, for example, the poly-RP, proteomics RP here, and also the proteomics HIC. We have a screening phase here. You can have the part number for your reference. And we have from our sales team, we have a 15% right now for the because of this webinar. If you want to have more information on the products, you can go into this link. We also do service screening as well. If you want to speed up your method development and don't know which phase to start with, we can take a look at your sample with our columns and then give you a head start. All right. I want to thank you. If you have any questions, you can contact us at tech support, or you can contact me directly. So this is also a promotion. Also, I'll be at the ADC Summit this October. So if you want to meet me in person, we can set up some time. Okay. And then before we go into a Q&A session, and our team's gathering all the information right now. So I would like to just have a 2-question poll before we go into the Q&A session. So the first one is want to understand the ADC project timeline needs. If you're currently working on the ADC, or if you expect, or if you don't work on the ADC at all, but these are the workflow actually can really apply to other method, other sample types as well. I will just wait for a few seconds for this question to finish. All right, and then here's we'll share the results here. All right, so we go into our next question. What are the current phases you're using or you plan to use? Okay, here is the answers for the second question for everybody too. So it's interesting. A lot of people, the 56% SEC and all the other phases getting to the ADC analytical characterization. All right, so here's our poll. We'll hide this, and then we'll go into the Q&A session. First question is, do you analyze low molecular weight fractions? Yes, you can, because it's apparently with MAB or ADC, it's all very critical for the product integrity. So you can actually use the single column, and then sometimes if you have a little bit closer to the monomer, sometimes the two columns in tandem, you can do the separation. So and also play with their conditions to have better separations as well. The second question is, okay, what's the Messianic spec paper? Actually, I think I have that in my reference section. Let me take a look at. All right, so we'll go into our reference section. This is the number 4. It's actually very well written with different denaturing condition, TFAs, acetic acids, and then the acetonitrile conditions, the modification there. So will you send the slides and the record webinar to us? Yes, definitely. We'll send you the link to our webinar and also along with the slides. So if you want to go back to some of the analysis conditions and also the column information separation profiles, you can take a look at those. Another question is, how does the screening service work? In general, we'll actually, before we start, we always will talk about your challenges, what kind of samples, what kind of sample information, what's the specific goals, and then we can look at the columns you are interested in, or even column or columns, so we can formulate a plan to move forward, select a movable phase to start with to give you a head start on your analytical method development. Another question is for prep purpose. What do you suggest to separate the conjugated and unconjugated antibodies? I think there are phases we talked about here. Clearly, Hick phase, you can see that the separation very well, and also depends on the workflow of your process. What kind of column technologies, and also depending on the difference between your unconjugated and the conjugated MAB. So for using the regular purification methods, you can take a look at IEX, SEC, and then the Hick. All these phases can be considered. Of course, for ACC, you get a very close molecular weight. It may not be possible. And for purification purpose, you probably have to consider it's under the native conditions. So Hick is, it's a great phase for the native condition separation. Okay, that's to our sales team. Is it possible to have the 15% off on the SEC column? I think, for this webinar, I think yes. I would say yes, because due to the webinar promotion, yes. Okay, so I think that concludes our webinar, and then just let us know if you have any questions, and let me just show you the contact information again, and again, I will be at the ADC Summit, so just let us know if you would like to talk to us and like to meet us to discuss your projects. I want to thank everybody for your attention, and I'm really looking forward to talk to everyone in the future. Have a good day. Bye.